Hi, in this video we're going to look at how mechanical energy can be conserved in a roller coaster as an example. So we have a 315 kilogram roller coaster car that reaches its peak at 33.0 meters. The ride pauses momentarily at the top of the first peak, which is point A, before releasing the car from rest and letting gravity pull it down. The height at point B is 12.5 meters and the car reaches the ground at point C. Assuming no friction, air resistance, or other external forces, determine the kinetic and potential energy at each location. So we're making a big assumption to say that there's no friction or air resistance here. That's not very realistic, but for the sake of simplicity, in this video, we're just focusing on how mechanical energy can be conserved in various scenarios. So in real life, of course, we would have some friction and air resistance that would kind of steal away some of that mechanical energy, turning it into heat and sound and vibrations. But for the purpose of this video, we're going to neglect that. We're going to just say that mechanical energy is conserved. So the total mechanical energy throughout the ride is going to be constant. And the total mechanical energy is the kinetic energy plus the potential energy. And that's what stays constant the whole time. So if we added up the kinetic and potential, we know it's going to be constant. Now we already know some facts about the kinetic and potential energy here, even before we get started. It said at the top of the ride here that the car paused for just a moment and then it was released from rest. So we know right off the top that the kinetic energy of the car at point A is 0. It started at rest. And then we also know the potential energy of the car down here at point C, the gravitational potential energy is 0 because it's reached the ground and we're defining the ground here to be 0. So what's left to do is just define the kinetic and potential energy at these other locations as needed. So let's start with the point A at the top here. We want to find the potential energy of this car, and we're talking about the gravitational potential energy, and that's equal to mgh, mass times 9.81 times the height. So we do that, we already know all the information from the problem. I'm looking at the top of the problem there. It says the mass is 315 kilograms. G, we're going to use 9.81 meters per second squared. And the height was 33.0 meters. So at this point, we just pull out a calculator. And as soon as I can get one, I'm using my phone to record, so I can't really use it as a calculator. So multiply those three numbers together, and if I did that correctly, I get rounded up to 102,000 joules of energy. And this is the total mechanical energy as well, because the kinetic energy is 0. So if we wanted to, say what the total is, 0 plus 102 is 102,000 is just 102,000. So we also know then at the bottom of the ride, the kinetic energy, since we haven't lost any mechanical energy due to the friction or anything like that, we know that the kinetic energy at the bottom is going to be equal to the potential energy at the top, because the total between the two must always be 102,000. So all that's left to do is at point B, we just need to find one of the two. We need to find either the kinetic energy or the potential energy, and then we can subtract and find the other one that we're missing. So what information do we have about point B? Do we know the speed or the height at point B? That'll kind of tell us which one we're looking for. And in the problem, it says a height. It says the height at point B is 12.5 meters. So I'm using that information. I will use the same values here, but instead I'm going to use height of 12.5. So I'm going to go back to my calculator here. Messed up. So we're going to do 315 times 9.81 times 12.5 is 38,626.875. I'm going to round that to 38,600. Okay, now to find the kinetic energy, it's simply just going to be it's going to be the total mechanical energy, which would be 102,000 joules, minus this potential energy, 38,600. And again, that's because we know that the total mechanical energy must be constant the whole time. So 102,000 minus 38,600 is 63,400 joules. All right, so there we have it. So if you added up the mechanical energy at each point, it would be 102,000 joules at every point. And that's what we get when there's no friction, when there's no external forces acting on our system here. So that's all I've got for you in this video. Remember, habit is the battleground of character.